Good morning, everybody. Am I audible to you?
Yes, sir. Good morning.
Yeah, good morning. Yesterday, we had started with the topic centrifugation, and I told you about some of the basic things about centrifugation. We have seen what are the different forces which act on a particular particle which is present in a liquid, and as it sediments down within the liquid, it will be acted upon by three types of forces. One is the force of gravity, the other is the force of buoyancy, and the third is the viscous drag. Okay, and then we have tried to see the mathematical representation of these three types of forces which are balanced together. Is it right? And then I told you about what is the concept of sedimentation velocity and the terminal velocity. So terminal velocity is when the particle doesn't experience any net acceleration, but it tries to settle down at the bottom of the container with a uniform velocity. That uniform velocity is called as the terminal velocity. Okay, then we come to another important aspect of the centrifugal force, and that is we already know that force is equal to mass into acceleration, isn't it? Now, if it is centrifugal force, and since it is a radial kind of a force, okay, the motion of the particles is in a circular form, and therefore this force, that is centrifugal force, which is denoted by Fg, is equal to mass into acceleration. But here the acceleration is actually includes the term angular velocity. Okay, angular velocity is omega, right? And this omega is represented in radian per second. Okay, that is angular velocity, and that multiplied by the radial distance of the particle from the center of the axis of rotation. Okay, so that is r. So centrifugal force is expressed like this: F is equal to mass into the angular velocity omega square r. Okay. So in other words, what we can say is the centrifugal force is dependent upon the angular velocity. More is the velocity, more is the centrifugal force. But the relationship is not, the relationship is like this, that the force, centrifugal force is dependent upon the square of the angular velocity. Okay. So when the square of the angular velocity increases, then there will be an increase in the corresponding increase in the centrifugal force. And this force is also dependent upon the distance of the particles from the center of rotation. Okay, so more is the radius, more is the centrifugal force acting on the particle. In other words, can I tell you that the bigger is the centrifuge machine, or bigger is the rotor of the centrifuge machine, the more will be the centrifugal force acting on the particle. Is it clear to you?
Yes, sir.
Okay, so there is a small problem for you just to understand this concept of angular velocity. Okay, so what is the applied centrifugal field at a point or at a particle which is placed 5 centimeter from the center of the rotation and which has an angular velocity of 3000 radian per second? Okay, so the formula is very simple. We have the centrifugal field is equal to omega square r. Okay, since mass of the particle is not given to us, we are assuming that it is a unit mass, that is 1. Okay, so the force is omega square r. Omega is given to us, that is 3000 radian per second. So 3000 square multiplied by the radius, that is 5 centimeter. Is it right? And then if you solve this particular problem, then it comes to 4.5 into 10 raised to 7. The unit is centimeter per second. Okay. Then coming to the centrifugal force in terms of the angular velocity. Okay, so did you know this, that 1 radian, do you know what is 1 radian? I've already given the definition here. It is the angle subtended at the center of a circle by an arc with a length which is equal to the radius of the circle. Do you want me to show it on the whiteboard?
Yes, sir.
So let me try it on the whiteboard. If I have a circle like this, okay, and then okay, I'll draw a point at the center. Maybe I'll show a very small circle here. Okay, so assuming that this is exactly the center, okay, and then we know that this is the radius. Oh, sorry. How do I undo? Okay, let me take a straight line, and this is the radius, isn't it? Shall I write it? R is the radius. Okay. And then what I'm trying to tell you is that it is one radian is equivalent to the size of the arc, okay, arc of the circle, which is equal to the radius. Okay, so let me draw another line here. Maybe something like this. Okay, and then what I'll do here is once again I want to copy this. No, I don't think I can do that. Okay. Can I not copy and paste it? I don't know. Okay, it is not possible. So I'll again put one R here. Okay, and then what I'm trying to say is the length of this arc, okay, the length of this arc also should be equal to R. Is it right? So length of this arc is equal to the radius of the circle. Okay, so now this particular arc is creating an angle here at the center. Let me again draw it with another color. Okay, this angle which is subtended by the arc, which is equal to the length of the radius, okay, equal in length to the radius of the circle, that angle, let me call it theta. Okay, so this angle theta, whatever degree it is, okay, theta degree, so this angle is called as 1 radian. Is it clear to you?
Yes, sir.
Okay. Okay, so I think I have to go out of this share. So now the angular velocity omega is now given as the number of degrees which are traveled, okay, number of degree, that is the movement of the particle, right, or the movement of the rotor per unit of time. Okay, so I've written here delta theta divided by t, that is the angular velocity. Amol wants to enter into the class, so I'm admitting him. Have you understood this? What I've written here, angular velocity is the delta theta. Delta theta is, was that? Somebody was trying to say something or there was some noise. Okay, so delta theta divided by t. So per unit of time, how many degrees is the movement? That is called as the angular velocity, right? But now, since we are talking in terms of the angular velocity, instead of using the term just delta theta, I'm going to say radian. Okay, how much radian is the velocity per second? Radian is what? One radian is what? It is the length of the arc. Okay, it is the angle
Angle.
angle subtended by the arc, which is equal in length to the radius, isn't it? So that is also
Yes, yes.
a degree. Okay, radian is nothing but degree angle. Okay, so instead of saying delta theta, I am writing here radian per second. How many radians the particle is traveling per second? That is the angular velocity of the particle. Is it okay? Which is undergoing centrifugation, of course. It may be a bacterial cell also. Okay, so if a bacterial culture is kept in a centrifuge machine, okay, and there is a rotor which has a particular, you can say, radius, okay, and then you are trying to centrifuge the particle. The particles are all, or bacteria are all moving in the centrifugal field, and the velocity of these particles will be given by radian per second. That is how much degrees in radian it is traveling per second. Okay, now in any circle, you know that there are 2 pi radians. So circumference of a circle is 2 pi r. So instead of saying 2 pi r, we are also, because radian is also equal to the radius, okay, the degree, in terms of the degree. So we are putting here, there are 2 pi radian in any circle. And therefore, if it is a 360-degree complete circle, then we have 2 pi radian. Okay, 360 degrees equal to actually 2 pi radian. And therefore, if you want to know how much is 1 radian, then 1 radian is actually equal to 180 divided by pi. Okay, in degrees, 180 divided by pi. Okay, so if you solve this particular equation, okay, 180 divided by pi, you know the value of pi, it is 3.14. Okay, so 180 divided by pi will give you roughly about 57 degrees. Okay, 57.3 or something, right? So 1 radian is equivalent to that many degrees. Is it right? Now for a complete revolution, if you are talking about, then then the delta theta, okay, delta theta is what? It is the amount in or the number in degree how much the particle is moving. Okay, so if it is one complete revolution, then that delta theta will be equivalent to 2 pi radian, isn't it? 2 pi radian. And therefore, if you are talking in terms of the velocity, then the velocity will be given by omega is equal to 2 pi radian per time, per unit time. Okay, 2 pi radian per unit time. Is it clear to you?
Yes, sir.
Okay, now if this same term we are going to express in terms of revolution per minute, because you know that in the centrifuge machine we are using this particular term, that is revolution per minute. Okay, so in terms of the revolution per minute, what we can write here is 2 pi. Instead of putting the term radian here, I am putting here revolution per minute. Okay, so 2 pi revolution per minute, but this is for how much? 60 seconds. Okay, time here is per minute, and therefore I have written 60 seconds here. Okay, so angular velocity can be given by 2 pi revolution per minute per 60 seconds. That is per minute. Now, if this term is put in the equation for the centrifugal force, then we know that centrifugal force is given by m into omega square r. Okay, so that will be equal to m multiplied by 2 pi square, so that becomes 4 pi square. Okay, 2 square is 4 and pi square is pi square here. Okay, so 4 pi square and revolution per minute square again, because this complete term is squared, this much, okay, multiplied by the radius, okay, divided by 60 square, that is 3600. So centrifugal force in terms of the angular velocity can be given by this expression, that is m, that is mass into 4 pi square revolution per minute square, r divided by 3600. Is it okay?
Yes, sir.
So again, there is a small problem for you, just again to understand the concept. So if I'm using an ultracentrifuge, an ultracentrifuge is operated at 40,000 RPM. So this 40,000 RPM will have what angular velocity? In terms of angular velocity we are talking about. Okay. So again, we can give here omega is equal to 2 pi revolution per minute per 60 second. Okay. And therefore it is 2 into pi, that is 2 into 3.14 multiplied by the revolution per minute, that is 40,000 divided by 60. Okay. And when you solve this, it comes to 4188.8 radian per second. So that is the angular velocity of the rotor. Is it right? So RPM can be converted into angular velocity, or angular velocity can be converted into RPM. Now, if the same answer here, 4188.8 radian per second, is to be written in terms of the g, okay, that is gravitational acceleration, then what we can do is just divide this number by 981. So omega square r, RCF is equal to omega square r divided by 981. So what is omega square? This number squared. Okay, so 4188.8 square multiplied by r. So just consider that r is equal to 1 centimeter. Okay, radius is 1 centimeter. Okay, and then that number, so square of this number divided by 981 will give you the RCF, that is the relative centrifugal field or relative centrifugal force. Okay, so these are quite simple problems, just for understanding sake of understanding sake, right? Then we come to another important term, that is called the sedimentation coefficient. Just a minute, let me see the slides first. Okay. Okay, so now we already know that force of the centrifugal force is given by m into omega square r. Okay, now as the particle sediments down, okay, as the particle sediment down in a liquid, along with the sedimentation, something called as diffusion is also going to happen. Okay, and because of this diffusion, we are going to replace the term mass of the particle. Okay, mass of the particle will not remain as such because there is diffusion force also, and therefore it is replaced by what is called as the effective mass. Okay, so effective mass is given by this term, that is mass of the particle minus rho minus volume into rho of the liquid, that is the density of the liquid. So volume multiplied by density of the liquid means what? It is the mass of the liquid which is displaced by the particle because of the diffusion which is taking place. Okay, so mass minus the mass of the liquid which is getting displaced, that quantity is called as the effective mass. Okay, so what is effective mass? It is the difference between the weight of the particle and the buoyant force due to the displacement of liquid. Actually, so do not to get worried, because whatever we have already seen yesterday, we are trying to again understand the same thing, okay, but in a little different terms. Okay, as such, there is no difference between what we have already seen yesterday and what I'm going to tell you today. But just for some you can say a better understanding about the sedimentation coefficient or the molecular weight of a particular particle, we are trying to slightly deviate from what we did yesterday. Okay, in a little different way we are going to understand the same thing, right? So here we have seen about the effective mass, right? V is the volume of the liquid which is displaced, and rho is the density of the liquid which is displaced. So V multiplied by P actually gives you what? The mass of the liquid which is actually displaced. Okay, liquid, that is the medium in which the particles are present, right? So the centrifugal force will now be like this. Okay, Fg is equal to, instead of putting just mass of the particle, we are putting the effective mass. Okay, to account for the diffusional factor or the buoyancy. Okay, so mass minus the mass of the liquid which is displaced, that is the effective mass, multiplied by omega square r, right? That is the centrifugal force. Now this centrifugal force is opposed by the frictional force. Again, we have seen this yesterday also. Okay, we have tried to balance the three forces. Which were the three forces? One was the force of gravity, with which the particle goes down into the container, okay, at the bottom of the container. The second force we had seen was the force of buoyancy. Okay, so again, that we have considered that force also here, but we have written, instead of, we have written it in terms of the effective mass of the particle. And then the third force that we had seen yesterday was the viscous drag. Okay, that is the frictional force, right? I have 10 minutes, so I'll try to finish something in 10 minutes. And if I cannot complete it, then again, immediately I'll start with the meeting once again. Don't go anywhere. And then today I'm not going to take a very long time. I'll only tell you about these one or two important equations, and then we will leave the lecture. Okay. Uh, so where was I? Yeah. So this is the centrifugal force, effective mass multiplied by omega square r. And then this force is opposed by the frictional force. And here we are writing frictional force in a little different way, although the meaning is the same. Okay. So frictional coefficient multiplied by the radial velocity. Okay. Because I should tell you that this frictional force is dependent upon the frictional coefficient of the liquid. More is the frictional coefficient of the liquid, more will be the frictional force. Okay, when will be the frictional coefficient be more? It will be more when the medium is more viscous. So yesterday also I have told you the same thing. Okay, so frictional force is equal to the frictional coefficient multiplied by the radial velocity. Okay, yesterday also I have told you that frictional force or the drag force is dependent upon the velocity of the particle. More is the velocity of the particle, more is the frictional force that it will encounter. Is it okay? So instead of putting just the linear velocity, because it is centrifugation, we are trying to write here radial velocity. Okay, so radial velocity, if it is more, that is if the rpm is more, then the frictional force also will be more. Okay, frictional force will be encountered by the particle. Okay, and that this term f multiplied by radial velocity can also be written in this particular form, that is f multiplied by dr by dt. What is dr by dt? It is the velocity with respect to time. Okay, change in position, displacement with respect to time, isn't it? But because it is a you can say an angular motion, okay, a rotating motion, it is velocity. Okay, because constantly there is a change in the direction, so it is a vector quantity, isn't it? So this frictional force is now given by this particular term, that is f, that is frictional coefficient multiplied by dr by dt. Dr by dt is what? Displacement of the particle in the rotational sense, okay, with respect to time. Is it clear to everybody?
Yes, sir.
Okay. Now, again, in the similar fashion that we have seen yesterday, again, we are going to balance the three forces. Okay, so centrifugal force is now balanced by the frictional force, and therefore the Fg is equal to Fd. Okay, and when there is a balance, when there is a perfect balance, then the particles will sediment with a uniform velocity, and that uniform velocity is called as the terminal velocity. there will be no net acceleration on the particle. Okay, so velocity of the particle will not increase, velocity will remain constant, but the particle will continue to fall to the bottom of the tube or in the radial direction. Okay, it will go to the in the radial direction from the center of the centrifugation, from the rotor to the end of the rotor, isn't it? From the center to the end. Okay, so that velocity will be uniform velocity, which we call as the terminal velocity. Okay, now when the forces actually balance each other, then we can write this equation like this: m minus vp omega square r is equal to f dr by dt. Do you agree with this? That is, fg is equal to fd. Okay, so fg, we have already written it here. Fg is equal to m minus vp omega square r. So the same thing I have written here, m minus vp omega square r, and that is equal to the frictional force, that is f dr by dt. So I've written it here on the right hand side of the equation, f dr by dt. So these two forces are now equal and opposite. Okay. Now what I'm going to do is just mind very well that this particular equation number 7, which we have already seen yesterday. Can you see this? 4 by 3 pi r cube rho p minus rho s into g is equal to 6 pi r eta and into the terminal velocity vt. Okay, this equation is exactly the same as this equation. We have only written it in a little different manner. The meaning is exactly the same. We are balancing these two forces here. Okay, so now what we do is we multiply both the sides by Avogadro's number. You know what is Avogadro's number? Who can tell me?
6.023 10 to the power 23.
Okay, but what is it? What does the number represent? Six 6.023 into
10 to the power 23.
okay, that's very good answer. Okay, you remember that number very well. But my question is, what does that number tell you? What is the what you can say meaning of that particular number?
Express the molarity.
Polarity.
Mole.
Hmm. So Avogadro's number. Yes, Shubhangi.
Molecular weight kilogram.
It is not the molecular weight. Avogadro's number is the number of atoms or molecules which are present in, say, 1 liter of, in 1 mole of any substance. Okay. So as per the definition, okay, 1 mole of any substance will contain Avogadro's number of molecules or Avogadro's number of atoms. Am I correct? Okay. You take 1 mole of NaOH, you take 1 mole of water, okay, they will contain exactly the same number of molecules, and that is the Avogadro's number of molecules. Is it okay? Okay. So now what I'm going to do is I'm going to multiply this equation on both the sides by N0, that is Avogadro's number. And therefore I'm writing the equation again, N0 m minus Vp, okay, is equal to N0 again f dr by dt divided by omega square r. So this omega square r term is taken from the left hand side to the right hand side, and therefore it will go into the denominator. Is it okay? And then I should tell you one more thing, that the velocity of the particle in a liquid will depend upon the size of the particle as well as the shape of the particle. Okay, and it is proportional to the applied force. The more is the centrifugal force, more will be the velocity of the particle. Less is the centrifugal force, less will be the velocity of the particle. But that velocity is also dependent upon the size and shape of the particle. Okay, if it is a perfectly sphere shaped particle, then it will have some velocity. But if the shape is deviating from the sphere, then it will probably have a different velocity. Okay, and that will also be based upon the frictional coefficient, or the frictional force which it encounters in the medium. Okay, and therefore what I'm going to do is I'm going to write this term velocity not as just equal to omega square r, but it will be I am adding this particular constant here, s. Okay, velocity is equal to s into omega square r, and this s is the proportionality constant here, and that constant depends upon the size and shape of the particles. So I'm accounting for the size and shape of the particles, which earlier we have not considered. Okay, earlier we have just put that angular velocity is equal to omega square r, but that was without considering the size and shape of the particle. Now, if we give due consideration to that particular aspect, then we should add one more constant in that equation, because the velocity is proportional to the size and shape of the particle. And therefore, velocity is equal to the constant s multiplied by omega square r. Right? And this particular s, okay,